Let's solve together 1999 AP Physics B FRQ question. So in this question, they say that a rectangular conducting loop of width W and height H and resistance R is mounted vertically on a non-conducting card as shown in the picture. The card is placed on the inclined portion of the truck and released from rest at the position P1. So here is position P1. It is at the height y sub 0. It has the width W and it has the height H. And here is the point P2. And then they have 0, and then the width 1, and then the width 2, and then the width 3. So they say that at point P1, at the height of y sub 0, above the horizontal portion of the truck, it rolls with negligible friction down the incline and through a uniform magnetic field B in the region above the horizontal portion of the truck. The conducting loop is in the plane of the page, and the magnetic field is directed into the page. The loop passes completely through the field with a negligible change in speed. Express the answers in terms of the given quantities and fundamental constants. So the first part, they say determine the speed of the cart when it reaches the horizontal portion of the truck. So for this part, I can use AP Physics 1 knowledge, where I have the potential energy going into the kinetic energy. So I have mg y sub 0 is equal to 1/2 m, and then the velocity at the bottom squared. So I have the velocity at the bottom is equal to the square root of 2g y sub 0. For B part, they say that determine the following for the time at which the card is in position P2 with 1/3 of the loop in the magnetic field. The magnitude of the EMF induced in the conducting loop that they have to calculate, and magnitude of the current induced in the conducting loop. So for this part, we can do that, use the formula for EMF. So for B, I have EMF is equal to the change of the flux over the time, and that will give me the magnetic field and then the area over the time, and that is magnetic field. The area is the height times the width over the time, and the width over the time is with the velocity at which it's moving, the one that we just found out, the velocity. So that will give me BH, and instead of W over T, I have the velocity that I just found. Maybe I'll just keep it in this color. And then I will plug it in, and I have BH. And then the velocity, I have the square root of 2g y sub 0 in terms of the variables that are given in this equation, or in this problem. So that is for my EMF. And if I want to find the current is going to be equal to the EMF divided by the resistance, and the resistance is given at the beginning, so the resistance mounted vertically. So I have the EMF, which is BH, the square root of 2g y sub 0, and divided by the radius. So that is going to be my current in the loop. And it doesn't matter that it entered 1/3 of the into the magnetic field, or 2/3, or as long as it's not fully in the magnetic field, it will have the current, and it will depend on the velocity at which it's moving, because you can see that EMF depends on this velocity. For C part, they say on the following diagram on the conducting loop, indicate the direction of the current when it is in position P2. So let's look at the position P before we draw our the current. So what happens here is it increases the magnetic field into the page. So the current will want to oppose the change. So the current will want to create the magnetic field that is coming out of the page and inside of the loop, and into the page outside of the loop. So the current is going to be in this direction if you use your right hand rule. So if I have the current in this direction, so I will have the thumb of right hand this way, and then my fingers are going to be curled that way, like this. So I'm going to have the fingers like that. And that shows the direction of the magnetic field that is going into the page and out of the page. So out of the page, into the page. And this will cancel the magnetic field that is already there. So there is a magnetic field going into the page where the loop is entering, and the loop will want to create the current that will oppose the increase of the magnetic flux in the loop. So they ask you to show the direction of the current in the picture that they provide. And let me see where the picture is. I don't see the picture here, so the picture was supposed to be here. So if you have in C, you should have had a picture right here, and the current would be going in this direction. So you would have to show the current in this direction or counterclockwise. And for D, they say using the axis shown, sketched a graph of the magnitude of the flux through the loop as function of horizontal distance x traveled by the card. The length x equals to sub-zero is to be the position at which the front edge of the loop just enters the field. Label appropriate values on the vertical axis. So every time they give you graphs and they say vertical, the axis, you have to calculate what the maximum flux is equal to and plug in that number. If it's the formula, it's the formula. And then for the second part, they say using the axis shown, sketch the graph of the current induced in the loop as the function of the horizontal distance x traveled by the card, letting x equals to sub-zero be the position at which the front edge of the loop just enters the field. Let counterclockwise current be positive and label appropriate values on the vertical axis. So the maximum possible flux is going to be equal to B times A, or it is BL and the width, or it's H and the width, right? So the letters that were given are H and the width. And so if I assume that this is my maximum value, so this is my maximum value, I have to label this value. Then when I'm going to reach the maximum, when the full width of the, so here I have the width of the first one, twice the width, 3 times the width, and 4 times the width. So if I go to my graph, this is the width of the loop, and this is the height of the loop, the width of the loop, and the height of the width of the loop. So I will have the maximum value of the flux when it is fully in the magnetic field, and it will stay there. If you see it's going to be until 3W, so it has to stay there until 3W. So for this length, the flux is going to be maximum, and the flux depends on the x, on the distance it traveled. So you see from here, the W is the x value, so it's linear relationship. So I have this way, and then by 4 it's going to be fully out, and there's going to be no magnetic flux. And then for the current, they say that you have to choose, let the current be in counterclockwise direction to be positive. And so if we graph our current, when the you're not gonna have current when the flux is not changing. So when the flux stays constant, there's going to be no current. So between W and 3W, I have no current. And then when it is out of the magnetic field, again, I'm not going to have current. So I'm only going to have current when it enters and exits. So in this case, I have counterclockwise direction positive and clockwise direction negative. So when it enters, it has counterclockwise direction, so that means it's going to have its maximum value. And then when it exits, so here is, maybe let's do a different color. So right here, when it enters, I have the positive counterclockwise direction, and when it exits, I'm going to have the opposite direction, because the current is going to be opposing of losing the magnetic field lines, so it's going to be in the opposite direction. And to calculate this current, we already have the value right here. So this is the value that I calculated earlier. So I can use them to mark my maximum negative and the positive. So for positive, my current is going to be BH, the square root of 2 G y sub 0 divided by R. And for the negative value, I'm going to have negative BH, the square root of 2G y sub 0 divided by R. So every time you have the graphs, you have to label your values. So I'm going to say this is this position, this is that. So this is my maximum current, and this is my maximum negative current. Thank you for visiting us today and for watching this video, and I'll see you in the next video.